My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Adda, I'd like to welcome you all to our International Physics webinar. And today it's our 56th International Physics webinar. So good evening to all here in Bangladesh, and good afternoon to all those who are connecting from Russia. I think you have already come to know that we have arranged a series of webinars, and we have successfully completed our 55th a few minutes ago. So now we are going to start our 56th webinar. So, and you have already come to know that today we are going to arrange a joint session between our department and the National Research Nuclear University MEPhI Moscow in a nuclear power plant technology. And we have another speaker with us here today, Dr. Alexander V. Nakhabov. And this is his second lecture in our international webinar. And he's currently working as an associate professor, Department of Nuclear Physics and Nuclear Engineering, Obninsk, Institute of Nuclear Power Engineering, MEPhI, Moscow, Russia. And he has already connected with us. So welcome, sir. And
okay.
Good evening.
Yeah. Dr. Pretam, thank you very much. Yes, I'm ready to start.
Yeah,
All's okay start with my presentation? Yes? Okay, so good evening in Bangladesh, I think. So today my presentation will be about monitoring, control, and diagnostic systems on nuclear power plants. Of course, its topic, it's not very big one, but very wide. So I'll try to provide main information in this area, first of all, for your understanding. So nowadays, first of all, you know, nuclear power plant, it's a very complicated object, complicated in technical sense. It's a lot of different systems, subsystems, different equipment working together. And of course, actually, it's very hard to provide uninterrupted work during 1 year or 1.5 years between outage periods. And of course, we are very concerned about possible defects. Defects in metal of pipelines, in equipment, and it can be defects like cracks, for example, different discontinuities, so-called discontinuities in material, or it can be, I don't know, some leakage, high vibrations, and many others, not defects, but abnormal situations. Of course, in all these cases, we want to find these situations preliminary, before some accident or before some destruction of some equipment and so on. And if you say about preventing defects on nuclear power plants, first of all, we should to say about non-destructive testing or non-destructive inspection. When we use different methods like ultrasonic, like radiography, like X-ray examination radiography, and liquid penetrant methods and others. And all these methods, as usual, should be provided during outage period. And if we will find, for example, some defects, we can organize repair as well in this time. But the second class of problems, as I said, there are actually abnormal states about leakages and so on. And problem is these abnormal states can be founded only during operation. Actually, it's no way to find possible leakage during outage period. Of course, maybe it will be some small defect in pipeline and we will see some leakages. But as usual, of course, the most dangerous all these situations will be during operation at nominal power output of nuclear power plant. So just to prevent possible accidents during operation, there are special systems. We can say about monitoring, control, diagnostic systems at nuclear power plant. On this slide, you see the list of these systems, not all, but maybe most important from the systems. All the systems actually can be considered like a separate block in overall instrumentation and control system of nuclear power plant, because in spite of big size of nuclear power plant as enterprise, as facility, there is one huge uniform information and computerized system just to monitor, control, provide different actions in this object. It's called instrumentation and control system of nuclear power plant. So actually, monitoring, control, diagnostic systems is just only one part of this huge overall system. But this part is very important for operation. First of all, we can say about in-core monitoring system. Actually, this system is included in this structure, but actually the system is maybe very different from others from this list, because in-core monitoring system, first of all, the system consists of a lot of sensors to measure temperature, to measure neutron flux inside of core, immediately inside of core. And this task actually is hard enough, because in VVR reactors, for core of reactor, actually all equipment is located inside of reactor vessel, and it means all sensors will be work in area with high neutron flux, with very high temperature and very high pressure. And of course, it's very hard to provide uninterruptible work of this equipment. But this system actually looks like actually monitoring system just to provide actual information for operators in control room. But all other systems actually, first of all, are designed to find possible violations in normal operation. So now I'd like just to briefly maybe comment all these systems for you, and to give you overall explanation of this idea, how to use these systems. We start from primary leak monitoring system. First of all, of course, every leakages from different pipelines and circuits, of course, these leakages can be some concern for us. But of course, possible leakage from primary circuit, for example, it's much more dangerous than leakages from some secondary systems, not only from secondary circuit, but maybe from some technical pipelines and so on. Of course, it's not a good event anyway, but first of all, of course, we are concerned in primary leak monitoring. First of all, I think you know about possible danger. If we have some leakage, it means there is some crack, for example, in pipeline, and some part of coolant just flow through this crack inside of containment building, for example. Of course, it means from one side, it means flowing of coolant. Of course, it's bad, because we need to provide some amount of coolant anyway inside of a reactor, just to provide adequate cooling of core, from one side. From other side, water coolant in the primary circuit, it's not usual water after several months of operation. Actually, it's like Olga said, it's actually high level radioactive waste, at least. And of course, in case of possible leakage, we will monitor some level of radiation higher than usual in some rooms or parts of containment. So it's these leakages are considering as some possible danger for our reactor installation from one side. Okay, you can ask me if these leakages so undesirable for us. Why we need special separate system to find these leakages? Because, for example, you can say, okay, let operator will use some instrumentation from the control room, because in the control room there are pressure gauges, there are different instrumentation to monitor state of reactor and state of core. First answer is actually it's just impossible to find small leakages, because yes, operator has access to see pressure in primary circuit. For example, in normal operation, this pressure should be, for example, 17 megapascals. And for example, if operator will see not 17 but 15, for example, okay, he will say, oh, it's possible leakages, we should to make something to prevent for coolant to leak in primary circuit. Yes, we can monitor this situation, but if operator really will find difference in pressure in 2 megapascals from 17 up to down to 15, it will mean we have huge leakage, because 2 megapascals difference means actually there is huge leakages from primary circuit, and of course it's too late to say about some prevention. In this situation, we should to say about accident, and we should to provide special actions, but to cope with accident itself. But our idea to find leakages on the early stage, when this leakage is very small, and you know, we will try to find situations when leakages too small actually to make some influence on operation, because it's a really early stage. But actually this leakages is enough in size for us just to be discovered using special sensors. So you see on this slide our goal: leakage monitoring and timely detection of coolant leak in equipment. First of all, we say about primary circuit pipelines, about pipelines between the reactor vessel and pressurizer, and for pipelines between hydroaccumulators of emergency core cooling system and reactor vessel as well. So 3 kind of pipelines, actually all 3 can be considered as primary circuit of nuclear power plant. And on this slide you see different modes. Our system should be ready to provide this detection in normal operation, in some operational occurrences, and in case of small break as well. When we say about usage of primary leak monitoring system, we use so-called leak before break concept. What does it mean? Actually, its concept and idea is very simple. When we say, okay, we arrange a lot of different sensors around of reactor installation, on pipelines, on equipment, just to find possible leakage during operation. Of course, we are very interested to find namely leakage, not full destruction of pipeline with huge flow of coolant through this place. Of course, our idea to find something small possible leakages and so on. So actually this concept was proved that for as I know, for majority of pipelines on nuclear power plants, this concept says that before big destruction of pipeline, this crack will be, growth of crack will be not very rapid, but this growth will take some time. So it means anyway we will have some time to find, first of all, small violation of sealing of pipelines, and then we can detect this leakage, and we can organize some protection by different actions just to prevent real accident, for example. So actually on this slide you see in this point, point number 4, about our idea to prevent unintended consequences from sudden rapid cracking and guillotine rupture, because guillotine rupture actually is the worst possible situation for pipeline, because in this case we say about destruction of our pipeline metal or welded joint in all section. So in one moment, all pipeline actually just cracks in two parts, and in this case, of course, we can say only about some mention of accident, because no prevention action possible in this situation. So next idea, the last state on this slide, conception is it's better to use not only one physical principle to find possible leakages in pipelines, but it's a very good idea to use simultaneously several channels. What does it mean? For example, on VVR reactors, actually three kind of sensors are used for one final purpose: acoustic sensors, humidity sensors, and radiation sensors to find level of radiation in different rooms or in volume of containment. Because task of detection of leakages is not so easy, and of course we want to have some high guarantee that we really find real leakage. In this case, we want to use several systems simultaneously. On this slide, you can see some example. All my pictures taken from official website of Dept company. It's a Russian company involved in development and production of different diagnostic system for Russian design nuclear power plants in Russia and abroad. Actually, excuse me, some explanation are given in Russian language. Of course, now I'll translate in English. So it's just example. You see, actually only pipelines of primary circuit, because on this slide there are no main circulation pumps in this place, and there are no steam generators in this place. We see only pipelines itself. So you see green triangles it stands for acoustical sensors, 12 pieces for this kind of system. Blue circles stand for humidity sensors, 18 pieces, and yellow triangles only one, I guess. It's acoustical transducer, special acoustical transducer, only one piece for some specific purposes. So our idea just to arrange sensors in not in every place of pipelines, because you see, first of all, on this picture, like some rows on pipelines. Actually, it's, I guess, that's welded joints. And of course, first of all, we want to find possible leakage through welded joints, because you know it's hard to imagine that possible leakage will start actually in pure metal of pipeline with no welding around and so on, because there is some probability of this event, but with high probability, of course, leakage will be realized through welded joints. So we will put a lot of sensors of different kind, acoustical or humidity ones, in different points of our primary circuit. On this slide, you see only 2 loops. You know, totally we have four loops of primary circuit. Actually, it's just example, because the same approximately pictures can be given for reactor upper block of reactor vessel itself, for pipelines between pressurizer and primary circuit, and so on. So it's just example for primary circuit itself. So first mechanism, first option to detect leakage by air humidity. So what is the idea? Actually, on VVR, all pipelines of primary circuit are closed during operation. All pipelines are closed from outer side by special thermal screens, special thermal insulation screens. It means, by the way, in case of leakage, it's just impossible to find this leakage by eyes from personnel, because actually all pipelines are closed, and you will see possible leakage only in severe situation, not in small leakage. So, but from our side, it's very convenient if we want to monitor humidity, because if you have pipeline and we have some thermal insulation screen around, with some small gap between. Actually, as I know, at least approximately 1 centimeter between insulation and metal. And in case of possible leakage, of course, what is mean leakage from primary circuit? It means that with very hot water under pressure from primary circuit will flow in this gap under insulation, and of course in one moment instantly this water get evaporated, so we will have only steam, water steam in this gap. And of course, if we have special sensors to measure humidity, and sensors are located alongside the pipeline, in this way we can using data from these sensors, we can monitor possible initializing of this leakage, and moreover we can get information about location of this crack, because location is very important. After detection of leakage, of course we should to say about approximately place of location for this crack, because we should after this we should to provide some repair. So location, the detection of location is very important too. So in this way we can monitor in the room if pipeline has no insulation, or under pipeline insulations. And you see the second variant is more preferable, because it's more effective from point of view of detection of leakage. So on this slide you see advantages of this approach. It's about this method can be used for bigger leaks. It means it's advantage, not drawback, because for other kind of sensors, in case of bigger leak, it may be like suppression of sensors, because it's very hard to get signals. But for humidity, it's not the problem. So this method are equally useful for small leaks and for leakage with bigger size. By the way, size of leakage means not geometrically dimensions of crack, for example, in millimeters. It means size in flow rate. About leakage, we say about this leakage is, I don't know, 10 liters per minute. So we say about leakages in terms of flow rates. We need no active systems to deliver air. Deliver air means possible compressors or something like these fans, just to provide airflow. In this case, there is no need in these kind of systems. It's enough just to have this gap of some gap between insulation and pipelines. Simplicity and low metal consumption for this system. The second option, to use acoustic signals. Acoustic signals, it looks like ultrasonic inspection in non-destructive testing, but with specific. Because in this way, idea is to use acoustical sensors. If we put acoustical sensor on the metal of pipeline, it means in case of possible leakage, we will have several acoustical waves in this system. First kind of waves, it's actually acoustic wave, sound and ultrasound in first of all in sound range, because it looks like real sound from kettle. And from one side, we can detect this sound signal from leakage and ultrasonic as well. But for us, it's much more important to detect not signal in gap, in air gap, but to detect signal accompanying ultrasonic wave in metal, because during leakage from pipeline, simultaneously it will be signal in air and signal in metal around this crack. And maybe you know, speed of sound, speed of ultrasonic speed in metal is much greater than speed in air. If sound speed in air approximately 330 meters per second, but for ultrasonic waves, with speed starting from 3000 meters per second. So of course it's more suitable if we use special sensors, to use acoustical sensors just to detect place of leakages. And as usual, it's enough actually at least two, of course, acoustical sensors arranged alongside the pipeline just to approximately detect location of leakages. You see adventures. In this case, we can try to separate several small leakages, one from another. And in this case, it's possible not to have some superposition signals from different leaks. I guess in humidity option, it's not the case, because for several possible links, of course, you know, several leakages from one pipeline, of course, is a very low probability event. But nevertheless, we should to keep in our mind different possible situations. So advantages of acoustic option to find possible several leaks, and fast detection and defining location. Because for humidity, you know, humidity it's inertial process, because humidity it's not so rapid process, because time of evaporation of water and time of propagation of this wave of high humidity, for example, of course, it's not so fast process. But for acoustical noise, it's very fast. It's faster than humidity. Moreover, for us, it's not problem, because you remember, acoustical and humidity subsystems actually are used simultaneously just to provide higher level of guarantee in case of leakage detection. But you see all slides about drawbacks of acoustic methods. First of all, we should think about background noise level, because when we say, okay, we will monitor some ultrasonic waves in metal of pipelines, it's great, but on operating nuclear power plant, I hope you know, there are a lot of usual normal vibrations, normal noises, and so on. And all these noises, of course, just form some background. Of course, if background noise level is rather high, of course, it's very hard for us to detect possible leakage on this background. So it's one problem. Acoustical method, it's hard to use in transients, because it's we can say about its normal method when we say about operation at one level of power output. For example, I don't know, 100% of power output, it's okay. But when we say about startup or shutdown, planned shutdown of reactor, in this case, for acoustic, it's very hard to find possible defects, possible leakages on these stages. This statement about a reasonable decision, we need experienced personnel. Actually, we say about this point for all systems, but for acoustics especially, because it's not so simple just to get information from signals, because we should to have specially trained personnel for this kind of systems. And yes, when we say about sensors, in this case, sensors should be installed by welding joints on the pipeline surface, and we need to provide special passages for cables from these sensors in thermal insulation. It's some kind of violation of thermal screens construction and so on. So it can be considered as a drawback of this system. So you see some overall information finally about this kind of system. So using this method of leak detection, we can define coordinates. You see accuracy. Accuracy is not so high. You see less than 50% of length between probes. So it can be considered as very big accuracy, but you should to keep in your mind that actually we have only this kind of methods to detect leakages, because yes, of course, in modern systems, developers try to minimize this accuracy. So minimize error and maximize accuracy, But anyway, as usual, for us in the initial stage, it's enough just to indicate part of pipeline. Part means part of pipeline between welded joints. It can be sufficient for first stage, because after this, thermal screens will be replaced from a pipeline, and we can use, for example, non-destructive inspection methods to find more precisely coordinates of defect in this pipeline. You see that acoustic and humidity monitoring considered as main physical principles. And about threshold of detection. So for acoustic leak monitoring, you see 3.8 liters per minute is considered as threshold of leakage detection. It means that if flow rate through leakage is less than this number, in this case, actually the system doesn't find this leakage. And this amount, about approximately roughly 4 liters per minute, of course, can be considered as big one for our point of view, like usual persons. But for primary circuit, of course, it's not big value, because we say about totally dozens tons of coolant inside of primary circuit. Of course, this amount is not so crucial for our system. Of course, for us, much more important to find as well leakages on this stage, because later, of course, if we will do nothing. In this case, of course, this crack will grow, and finally, as I said, we concern about destruction with huge flow rate through this destruction. And you see for our pipelines, this number for primary circuit, and these numbers for connecting between pressurizer and reactor, and for pipelines of emergency core cooling system. And the second requirement to the system's time lag. Time lag between time of leakage, initializing, and time of detection. Because, of course, we want to find possible leakage as soon as possible. In this case, this lag approximately 3 minutes. 3 minutes to find leakage itself leakage, and 7 more minutes to define coordinates and location. And you see for humidity, we see in this manner some thresholds for humidity subsystem. Okay, it's all about leak monitoring systems. The next very important diagnostic system on nuclear power plant. It's loose part monitoring system. What does mean loose part? Actually, we can say about loose or free parts inside of reactor installation. What does mean? Actually, free part means some object. Free means without no fixing. Some object inside of pipelines or equipment, inside of main circulation pump or steam generator or reactor vessel. Of course, in normal operation, it should be no free objects inside of system, because every free object are very dangerous because, for example, if this object are small enough to go through core buffle or core barrel, excuse me, inside of core, in this case, of course, this part, I don't know, some part of metal or so on, actually just can stuck in between fuel rods, for example, and in this case we will get overheating in this place and possible melting of fuel. And about origin, possible origin of these loose or free parts, actually it can be some objects just lost during repair. Nowadays it's rare, but some times ago on different nuclear power plant it were some cases. For example, different instrumentation just was lost inside of equipment, because equipment is huge, and in some situations repairing personnel can just lost something like screwdriver, like different instrumentation, and of course during operation it can be some source of very serious incident. From our side, it can be details of some hardware fixing. For example, in main circulation pumps, there are bolt connections between parts. And during operation, main circulation pump vibrates, strongly vibrates. It's considered as normal situation. But in case of poor connection, of course, for example, nuts from this bolt connection just can be free and just drop inside of circuit, and then it can be a reason for some problems. About loose parts, not free but loose parts, we can say, for example, about fuel assemblies or fuel rods, because in case of damaging of fixing, because all fuel rods are fixed inside of fuel assemblies in several points by point welding. In case of damaging of this connection, of course, situation is possible when some fuel assemblies, for example, just lose connection in some part, in upper part, for example, and in this case, in flow of coolant, our fuel assemblies will stuck around in different objects, and of course it's very dangerous situation as well. So especially to find this kind of states, of technical states, loose part monitoring system is used. So you see on this slide, first of all, noise anomaly, shock produced by loose or poorly fastened object, as I said. It means we will see propagation of acoustic waves in metals as well, like in leakages in primary circuit, when we say about acoustical waves in metal of pipelines. In case of some object inside of circuit, of course, every shock between this object and different elements or walls of equipment or pipelines will accompanied by propagation of acoustic waves. It's acoustic waves, I guess it's very hard to detect by our ears, by personnel. But if you say about special sensors, it's not the problem to detect these signals. So you see impact of signal of this system, and we should to realize continuous monitoring. You see, this sensor should to make conversion of signal from acceleration into voltage, and then we can calculate square value, for example, for this signal, and so on. And based on preliminary training of our method, we can make some thresholds to detect really possible free objects inside of reactor vessel. Of course, we say about event recording, because for all systems, like black boxes on aircraft, our task not only to find something like right now in this moment. Of course, it's highly desirable to find possible defects or leakages or free object in time of operation. But anyway, it's very important as well to have some recording of event, just to provide possible research and investigation after operation, because different situations are possible. You see saving of a main computer hard drive, like some storage. And of course, it's very desirable for system to provide some diagnosis. Diagnosis means in terms of a loose part monitoring system, we should to say about, for example, free object with mass, I don't know, several grams was detected. Because the most important parameter maybe it's mass of this object. Because depending on mass, we can say about possible dangers. Because if we say about free object 1 gram of mass, it's one situation. If we say about, I don't know, 100 grams, of course, it's a much more dangerous object for our equipment. Because a lot of different elements can be not destructed, but damaged by this object, finally. This abbreviation, it's actually instrumentation and control management system, upper level computing complex. It means that all our systems, as I said, working not separated, but in one, I don't know, like cloud, because we have every time some interchanging of data between different kinds of systems. Okay, I'd like to make accent only on several points here. So actually, this information was presented on the previous slide on scheme. So on this slide, you can see example of arrangement of sensors for this kind of system. You see different loops. So one section of reactor installation between loop 1 and 3, and another one between second and fourth. And you see, like hammer, actually, it's actually where are testing hammers. Testing hammers just to initialize some test shock on pipeline. And in this case, we just should to monitor signals on different sensors. It's actually some preliminary testing of this system. And you see, before entering in reactor vessel, before entering in steam generator, and so on, some key points of circuit from this point of view. You see on this slide some thresholds. In this case, we say about thresholds for mass. So system should find object with mass more than 0.05 kilograms. Actually, it means more than 50 grams. So lighter objects can be undiscovered. And if you say about loose parts, in this case, it's useless to say about mass. In this case, we should to say about energy, on energy of shock from this loose part in joules. So some strange number, 0.68 joules, but nevertheless with threshold to detection of free parts inside of reactor. Okay, I'd like to skip the slides because we have not so much time for my presentation. It's actually about some insight methods of analyzing, because when we say about data analysis from loose part monitoring system, of course we should to say about using different statistical or mathematical methods like correlation, spectral analysis, and so on and so on. So on this slide you will see only this information. And example of software. In this case in Russian language, as I know, for foreign power units, of course, interfaces will be provided in English or some local languages. So we can monitor signals, spectral form or time form of signal. We see layout of system with all sensors indicated, and moreover we can get access to raw data from different elements, in volts, in grams, we will see real signals and so on. It's first of all to provide some help for operators. The next system, vibration monitoring. Vibration monitoring maybe is most common from all the systems. Most common means not specific nuclear monitoring system, but I guess it's maybe obvious for you that vibration monitoring is very important in very different areas. But first of all, vibration on nuclear power plant, first of all, we are concerned about vibration in rotating equipment. When we say about main circulation pumps, other pumps, because in general on nuclear power plant with VVR 1200, there are more than, as I know, 200 of pumps, different pumps. So huge number of different sizes and so on. And of course, we should to say about turbine. Turbine rotor will rotate with very high speed, and of course, vibration of turbine can be very dangerous for all nuclear power plant. Finally, and in usual life, really used as example, I don't know, washing machine in your homes. You know, high vibration as usual will say about some problems in our construction, with bearings, with shafts, with possible misfunctions and so on. Our task just to detect, as usual on your stage, this trend of changing of this vibration in some wrong side, first of all. So we can use special sensors just to monitor this parameter. So like example, you see on this slide, a main circulation pump, 4 units from 1 power unit of VVR, huge hydraulical part and electrical engine of this main circulation pump with shaft between. Of course, there are several bearings in this system, and we want to monitor vibrations during operation of these pumps. We use sensors, special preamplifier packages, because it's specific, some feature of many diagnostic systems, because the systems allocated sensors inside of reactor or nearby of reactor vessel or pipelines and so on. But computers and moreover control rooms, of course, are distant in several dozens, maybe 100 meters away. Of course, we should to provide not transportation, but you provide signal between sensors up to final computer. As usual, we should use special preamplifiers. And you see industrial personal computer, like example, Advantech, with input analog input card and so on. The next kind of system sounds very similar, not vibration, but vibration noise monitoring. Actually, only one word noise actually means totally another system, because vibration noise monitoring system, first of all, is designed to monitor possible vibration of reactor internals. Reactor internals, it's fuel assemblies, first of all, core barrel, and maybe fuel rods inside of fuel assemblies. So in normal operation, all these elements should be fixed, should be secure, fixed in special positions with different connections system. But during operation, it's possible to lose this connection, and as I said previously, we can monitor some abnormal vibration. For internals, reactor internals, of course, this task is very important, because actually we have no other way to monitor this kind of dysfunction, because reactor vessel is closed. It's closed under pressure, and actually we have not so much instrumentation to monitor situation inside of reactor vessel. So monitoring of vibration is very important in this sense. So example of the system, some of examples. We use different kind of sensors, relative movements, absolute pressure, ionizing chambers, because we should to measure not only mechanical vibrations, but we'd like to use special instrumentation like ionization chambers to detect neutron flux, because surprisingly, fluctuations, changing of neutron flux in the reactor contains information about possible vibrations of internals. So these phenomena are interconnected. And direct charging sensors, ionization chambers, are located around of reactor vessel in biological protection. And direct charging sensors actually are located inside of core to measure neutron flux in different points of core. So yes, so finally, as usual, we will get spectra. So dependency between signal power is very roughly versus frequency. And as usual, we will have a set of examples of normal operation, how spectra should look like in normal operation situation. And in case of emergency, we will find some abnormal peaks on spectra and so on, some kind of this violation of normal operation. And very important, especially for this kind of system, from one side, vibration noise monitoring systems are installed on many VVR of different power output and so on. But from other side, every power unit are unique. Unique means details of characteristics, details of features. In this sense, for every power unit, this system should be installed before startup and should be tuned. For specific of this power unit. As well, I guess the same will be made for Rupur nuclear power plant during construction. On this slide, you see possible source of vibration. Actually, as I said, relaxation of some members and so on and so on. 2 points in Russian. This means slight boiling of coolant. Slight means not boiling in all volume of core, but in several several channels between fuel rods, for example. So small slight boiling of coolant and curving of fuel assemblies. Curving means changing of form from cylindrical ones. So you see, actually, there are a lot of possible reasons for vibration or some violation of geometry or parameters of core in reactor. And as I said, we have ionization chambers, 8 pieces. We have with LAN, it's a uniform network of nuclear power plant. We have signals from sensors, through terminal boxes to special calibration unit, amplifiers, and so on. And finally, we have actually information from all sources just collected in one special device, like special technical computer, just to process all this information together. And actually, finally, yes, finally, I'd like to say about overall picture of different systems, because today I have actually very small time to explain maybe basic idea. And on this slide, you see so-called online monitoring, control, and diagnostic system in one connection, maybe, because all the system, as I said, are not isolated. All the system work together during operation. So you see vibration noise, special system automated residual life monitoring, loose part, main circulation pump, technical diagnostic. Actually, it's vibration. So we have special unit integrated diagnostic system. And on this slide, you see different connection between parts of systems and provided information in different subsystems or vice versa. For example, you see in core instrumentation and neutron flux control equipment. Actually, we have some flows of information between different parts of reactor installation subsystems. And then we have systems to provide information of upper level. Industry diagnostic, upper level control system, finally control room for operators. So nowadays in Russian design nuclear power plants, all these systems are working together. And moreover, in our country, many power units, not inside of one nuclear power plant, but power units of one type of VVR, for example, actually are connected between in one network in our country. Because we have some headquarters in Moscow. In case of possible accident situation, in this case, we will have possibility to involve highly trained specialists from different areas just to solve this problem. Because, you know, it looks like online diagnostics, but not through internet, of course, through special transition lines. But nevertheless, idea is to provide some global system, not global, but in one country, to realize diagnostic of power units during operation, just to increase safety and reliable work. So that's all. Thank you very much. I started to put this presentation in this time frame.
Thank you, sir, for your nice presentation and very informative. So I think students have learned a lot of things. So we have questions. So if you allow, we can start the discussion. Okay, so when does the huge leakage occur, and how many period of days need to repair it usually? And the whole unit need to shut down.
Shut down for what kind of operation?
So the okay, so I can repeat the question. So when the huge leakage occur, and how many period of days need to repair it usually? And the whole unit need to shut down.
So,
for this.
if I understand right, the question is about, first of all, for leakage monitoring system. Yes. And how much power we need?
Нет, здесь, смотри, если огромный огромный ликидж встречается, как долго этот можно восстановить, на какое время это утечку можно восстановить?
Thank you, Olga. So, if we understand right, yes, question is about how much time needed to restore
leakage
flow in case of possible leakage. Yes.
Yeah. When does the huge leakage occur, and how many period of days need to repair it?
It's a good question. It's a good question. Of course, you know, it depends on leakage, because when we say about, for example, guillotine rupture of primary circuit pipeline with all section, from one side, it's a worst situation, and for VVR 1000, at least several years ago, it was considered as maximal design accident. It's actually destruction of primary circuit pipeline. Happily, in every VVR and PWR in the world, for many years, it was no one case of full rupture of primary circuit pipeline. And in this sense, for usual it means, you know, anyway, it's rare leakages, because leakage from primary circuit, it's a rare event. It's not every year, at least. But in these cases, as I know, I guess the power unit should be shut down, because as I know, you have no possibility just to shut off this part of pipeline from flow of coolant. So we should to shut down power unit and to provide repair. I don't know, several days at least, I guess. So in case of leakage from really main circulation pipeline, we need several days to provide shutdown, repair, testing, and then after some approval documents, we can just again start up power unit. So it's not hours, it's not minutes. It's actually several days at least. In case of really, I don't know, severe damage. Of course, we can say about months, but as I know, it's not the case.
Thank you, sir. So in monitoring a nuclear reactor, can you use neutrino to monitor the nuclear reactor?
Neutrino?
Yeah.
It's a good question. For me, I'm closer to engineers, not to physics specialist. Anyway, I heard about neutrino diagnostic in nuclear power plants because in our university in MEPhI, of course, there is some specialization. Some departments, first of all, involved in questions of practical operation of nuclear power plants and so on. And of course, there are not theoretical departments, but I don't know, to provide some research on the frontier. And I heard about this. Right now, I had no answer. I heard about it's possible to use neutrino, but it looks like some very modern and very new method. I'm not sure this method is well proved nowadays, but I guess yes, it's very interesting area, and I know my colleagues from Moscow side of MEPhI, some colleagues are involved in special research and development works in this area, how to use different physical particles, different physical properties for reactor diagnostics. Because you saw really diagnostics on nuclear power plant, it's a rather engineering question, not very physical,
Thank you, sir, for your nice presentation and the discussion session. And thanks, madam, also for joining us both the session. So we'd like to say thanks to both of you on the behalf of the Department of Physics, Pabna University of Science and Technology. It's actually it's my pleasure and honor for me to host you in our International Physics webinar. So thanks again, and hopefully near future we will arrange another webinar with you. And after COVID, so we'll invite you in our university for a face-to-face session. So thanks again. Bye for today.
Yeah, thank you very much, Dr. Pretam. Moreover, I'd like to say we are very interested in collaboration with your university. And moreover, I guess we will start to discuss with my colleagues different ways of our possible collaboration, not only with short lectures, but maybe some short educational models. Like, for example, one course can be provided in 1 week for your students. So different options available. So I think we can discuss it later with you, our possible ways. Because for us, it's very interesting to see your interest from you and your students. Okay, I hope you hear me.